In this episode, we build a beginner-friendly toolkit for talking about risk in a way that is concrete enough for engineers and clear enough for leaders, without pretending that uncertainty disappears just because you used a few numbers. Security and reliability discussions often collapse into vague phrases like low risk or high risk, and those phrases fail when people need to make hard choices about time, money, and safety. The terms in the title are popular because they help you describe uncertainty, failure behavior, and recovery behavior using a common language that is less emotional and more measurable. Monte Carlo is a technique for exploring uncertainty by simulating many possible futures, and the other terms are reliability measures that describe how often things fail and how quickly you recover. The core skill is not memorizing definitions. It is knowing when each idea helps and how to explain it without misleading people. When you can connect these concepts to decisions, you stop talking about risk as a feeling and start talking about risk as a manageable engineering problem. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Begin with reliability metrics because they are easier to visualize, and they support many risk conversations even outside security. Mean time between failures, MTBF, is a way to describe how often a reparable system experiences failures, on average, over time. Mean time to failure, MTTF, is similar but usually applied to non-reparable components, describing how long they last before they fail and are replaced. Mean time to repair, MTTR, describes how long it takes, on average, to restore a system after a failure, including diagnosing the problem, fixing it, and returning to normal operation. Mean time to detect, MTD, describes how long it takes to notice a problem after it begins, which is especially important in security because attackers often rely on not being detected quickly. These terms become powerful when you see that risk is not only about whether failure happens, but about how often it happens, how quickly you notice it, and how quickly you recover. If you have frequent failures but rapid detection and repair, the impact may be manageable. And if you have rare failures but slow detection and repair, a single event can be catastrophic. To keep these measures honest, you must understand what an average really means and why averages can hide dangerous patterns. An average is a summary of many events, and it does not guarantee that the next failure will happen at the average time. For example, an MTBF of 100 days does not mean you will get one failure every 100 days like clockwork. You could get 2 failures in 1 week and then none for months. This matters in security because incident frequency is often uneven and driven by external forces like new vulnerabilities, new attacker campaigns, and seasonal business changes. When you use MTTR, you also need to be clear about what counts as repaired, because a system might be technically online while still operating in a degraded or unsafe mode. For MTD, you must define what it means to detect, because noticing a strange log entry is different from confirming an incident and containing it. Clear definitions prevent you from presenting a number that sounds precise while actually mixing different kinds of events. Now connect these measures to security risk, because beginners sometimes separate reliability from security as if they are unrelated. In many real situations, security incidents behave like failures. Something breaks, service is disrupted, data integrity is threatened, and recovery work is required. Attackers also create failures intentionally, such as denial of service conditions or disruptive ransomware. Even when attackers are focused on stealth rather than disruption, the relationship between MTD and risk is direct, because the longer an attacker is present, the more opportunity they have to move, escalate privileges, and extract value. A shorter MTD often reduces impact, even if it does not reduce the number of attacks attempted. Similarly, improving MTTR reduces downtime and reduces the window in which the organization is operating in a vulnerable, unstable, or degraded state. When you explain risk using these measures, you give people levers they can actually pull, such as investing in detection capabilities, improving incident response procedures, or designing systems that recover cleanly. At this point, bring in Monte Carlo, because it helps you deal with the uncertainty that makes simple point estimates risky. Monte Carlo simulation is a method where you define uncertain inputs, such as how often failures occur or how long repairs take, and then you run many randomized trials to see a range of possible outcomes. Rather than producing one answer, it produces a distribution of answers, showing what is common, what is rare, and what is possible. For beginners, you can think of it like rolling dice thousands of times, but instead of dice, you roll random values for failure frequency, detection time, repair time, and impact. The result is not a prediction of exactly what will happen. It is a way to see how uncertainty and variability shape overall risk. This can be especially useful when leaders ask for certainty that you cannot honestly provide, because you can say, here is the likely range and here is the chance of a really bad outcome. To use Monte Carlo responsibly, you must start with a model that is simple enough to explain and transparent enough to critique. The model needs inputs, assumptions about how those inputs vary, and a way to calculate outcomes of interest, such as total downtime per month or expected number of incidents per year. If your inputs are fantasy numbers, your simulation results will be fantasy numbers with prettier charts, so the quality of inputs matters. A good beginner approach is to use ranges rather than precise values, such as saying repair time is usually between 1 and 4 hours for a certain kind of outage, with rare cases longer. You can also use historical observations, even if imperfect, to shape inputs, like past incident logs or maintenance records. The important part is that your assumptions are explicit, because Monte Carlo is valuable precisely because it forces you to state what you think you know and how uncertain it is. When someone challenges the result, you can point to the assumption and adjust it, rather than arguing about feelings. Now connect the simulation idea back to MTBF, MTTF, MTTR, and MTD, because these measures can become inputs to your model. For example, you might treat time between failures as a random variable influenced by MTBF, while repair time is influenced by MTTR and detection time is influenced by MTD. In a simple simulation, each trial might generate a set of incidents over a period and assign each one a detection time and repair time, then compute total impact. This lets you see, for example, whether improving detection by half reduces overall risk more than improving repair by half. It also reveals sensitivity, meaning which variable has the largest effect on outcomes, which helps you prioritize investments. This is one of the clearest benefits of Monte Carlo for security discussions, because security budgets often fight over priorities, and a sensitivity view can show where changes actually matter most. Even if the exact numbers are uncertain, the direction of impact can be informative. Because these measures are often misunderstood, you should also learn common misconceptions so you can avoid misleading people. One misconception is that a higher MTBF automatically means low risk, but if MTTR is extremely long, rare failures can still create huge harm. Another misconception is that reducing MTTR alone solves the problem, but if MTD is long, you might not start repairing until the attacker has already caused deep damage. Some teams focus only on prevention and assume detection is a sign of failure, when in reality detection is a control that reduces impact and improves resilience. Another misconception is treating MTTF as something you can change by willpower, when in many cases it is governed by component quality, environment, and usage patterns. In security, the equivalent mistake is assuming attacker behavior follows simple averages, when attacker campaigns can spike unpredictably. Clear risk communication requires you to state what the metric captures and what it does not capture. It is also vital to keep the difference between reliability events and security events in view, because the same measure can be interpreted differently. A hardware failure might have a relatively stable pattern, while security incidents may cluster due to new vulnerabilities and active exploitation. That means your model must consider that rates can change over time, and averages from last year may not apply next month. This is where Monte Carlo can be extended by using different scenarios, such as a normal period versus a high-threat period, rather than assuming a single stable rate. Even if you keep the model simple, you can still communicate that the numbers are conditional, meaning they depend on threat environment, change rate, and operational maturity. That honesty actually improves trust because it shows you are not pretending to know what cannot be known. Leaders can handle uncertainty better when it is structured rather than hidden. When you present these concepts to leaders, clarity comes from linking them to decisions and outcomes, not from reciting definitions. If a leader asks, "How risky is this system?" you can reframe the question into measurable elements. How often do we expect disruptive events? How long until we notice them? How long until we recover? And what does the impact look like during that time? Then you can use the metrics to explain the current state and the improvement path, such as reducing MTD through better monitoring and reducing MTTR through better recovery procedures. If you have a Monte Carlo model, you can say that most months will look like this range, but there is a smaller chance of a severe month, and here is what reduces that chance. This approach supports decision-making because it makes risk feel like a set of controllable variables rather than a mysterious threat. It also helps prevent overconfidence because you are showing a distribution rather than a single number that may be wrong. Another important use is to communicate risk trade-offs across different designs or operational approaches. Suppose one design has higher complexity, which might reduce MTBF because more can break, but it might also reduce MTTR because redundancy makes recovery faster. Another design might be simpler, with fewer failures, but when it fails hard and recovery is slow. Without a framework, people argue emotionally about which feels safer, but with these measures, you can describe how each design behaves. Monte Carlo can help compare them by running the same uncertainty assumptions across both designs and looking at outcome distributions. The result is not a final answer, but a clearer conversation about what kind of risk you are willing to accept. This is especially useful in security engineering, where perfect security is impossible and choices often involve balancing different failure patterns. You should also learn how to keep these methods from being abused, because numbers can create false confidence if used carelessly. One abuse is presenting a model's output as certainty rather than as a structured view of uncertainty. Another abuse is hiding weak assumptions, like using unrealistic repair times or ignoring detection delays to make results look better. A third abuse is focusing on the average outcome while ignoring tail risk, meaning rare but extreme outcomes that could be mission-ending. Responsible risk communication includes showing that rare events exist and explaining what controls reduce their probability or their impact. In security, tail risk matters because adversaries often aim for high-impact outcomes, not average ones. If you can explain both typical outcomes and worst-case possibilities, you help leaders choose investments that make the system not just efficient but survivable. The heart of the lesson is that Monte Carlo and reliability measures are tools for explaining risk with precision and honesty, not tools for hiding uncertainty behind math. MTBF and MTTF help you describe how often failures occur. MTD helps you describe how long you are blind to problems, and MTTR helps you describe how long you are in a damaged state. Monte Carlo helps you take uncertainty in those values and explore what a range of futures looks like, which supports better planning and better prioritization. When you use these concepts well, you shift risk conversations from vague fears to concrete levers, improve detection, improve recovery, reduce complexity, or invest in quality where it matters most. That is what it means to explain risk clearly in an engineering context, and it is a core competency for anyone who wants to make security decisions that are credible, defensible, and grounded in reality.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.